The following moles and titration question is about finding the molecular mass MR of an organic acid T. So a student was given a sample of an organic acid T and asked to determine its relative molecular mass and suggest its molecular formula. The first thing that is done is a sample of the acid was placed in a previously weighed container and reweighed, and the mass of the container and the acid is given. It's given as 8.25 grams. You're also given the mass of the container, which is 6.74 grams. So in the next part A, you're asked to calculate the mass of the acid used in the experiment. So what you're going to do is you're going to simply subtract the two values, remove the mass of the container from the first value, which is the mass of the container plus the acid. And if you subtract the two values, you're going to get the mass of the acid, which is going to be, so we're going to find the mass of the acid by subtracting the two values. And this comes out to be equal to 1.51 grams. So that is the amount of acid that is being used in the reaction. This acid is organic acid, is called T. Moving to the next part, the question reads that the student then transferred the sample to a beaker and added 50 cm³ or 1 mole per decimeter cube of sodium hydroxide. So you're transferring it to a beaker and then adding 50 cm³, 1 mole per decimeter cube sodium hydroxide, and the contents of the beaker were allowed to react and then transferred to a volumetric flask, and after that the mixture is transferred to a volumetric flask, and the solution was made up to 250 cm³ with distilled water. So in the volumetric flask you're making a 250 cm³ solution by adding distilled water, and this was called solution S. So we're going to make a rough sketch about this paragraph to note down what the steps to note down all the steps that are being taken. So here is a beaker. So this 1.51 grams of organic acid T, 1.51 grams of the organic acid T are being placed in the beaker, and after which to a beaker and added to 50 cm³ or 1 mole per decimeter cube of sodium hydroxide. So you are adding 50 centimeter cube of 1 mole per decimeter cube sodium hydroxide. So 50 centimeter cube, and the concentration is 1 mole per decimeter cube sodium hydroxide, which is NaOH, that's being added. And once this happens, the contents are then transferred to a volumetric flask. Once the reaction between this acid and this alkali over here finishes, the contents are then transferred to a volumetric flask. So we are transferring the contents, the leftover after the reaction, whatever is left over is transferred to this volumetric flask, and by adding distilled water, a 250 centimeter cube solution is made. So they react and then transferred to a volumetric flask, and the solution was made up to 250 cm³ distilled water, and this was called solution S. So this is our 250 centimeter cube, and this is called solution S. So by adding distilled water to the contents in the beaker and transferred to a volumetric flask, by adding distilled water you make up a 250 cm³ solution, which is called S. After which what happens is that 25 cm³ of S is now transferred to a conical flask. So we're going to now transfer 25 cm³ of S to a conical flask. So I'm going to transfer 25 cm³ of S to this conical flask over here. So only 25 centimeter cube of S is transferred to this conical flask, after which what the question says is that a few drops of phenolphthalein indicator were added to the conical flask. So we're going to add a few drops of phenolphthalein indicator to the conical flask. Just a few drops. Phenolphthalein is added. Phenolphthalein, remember, is an indicator, and that indicator is being added to this conical flask, and 0.1 mole per decimeter cube of hydrochloric acid was placed in a burette and added to the solution in the conical flask until an end point is reached. So he's titrating whatever is in the conical flask by putting 0.1 mole per decimeter cube of hydrochloric acid in a burette. So we're now going to draw a burette. So here is my burette. This is the burette, and he's filling it with 0.1 mole per decimeter cube of hydrochloric acid, which is HCl. And this HCl is being run from the burette, and it's being reacted with 25 cm cube of S. So he's also given us that he's given us the color of the phenolphthalein. Phenolphthalein is he said that it's colorless in acidic solution and it's pink in alkaline solution. So we're going to go over our steps once more. The first thing that was done in the experiment was that T over here, 1.51 grams of organic acid T, was dissolved in 50 cm cube or 1 mole per decimeter cube of NaOH. Remember, this NaOH is in excess, so at the end of the reaction, once this acid over here reacts with this alkali over here, salt is produced, but some of the NaOH would be left behind at the end of the reaction. And this leftover solution is then transferred to this volumetric flask. So this volumetric flask would also contain the leftover NaOH. So it's going to contain the salt plus the leftover NaOH that was produced in the previous reaction, and you ended up making a solution which had a volume of 250 cm cube by adding distilled water. So this solution over here contains the leftover NaOH from the previous reaction, and then 25 cm cube of S was transferred into a flask. So this solution over here also contains NaOH, the leftover NaOH from the first reaction that we mentioned, and you are adding phenolphthalein to it. Now, he's clearly said that phenolphthalein is pink in alkaline solutions. So initially, the color of phenolphthalein over here would be pink because the solution in the flask over here, the solution is basically containing the NaOH, the leftover NaOH from the first reaction. So it contains NaOH, and when you start adding HCl to NaOH, HCl is going to neutralize this alkali, and once all the alkali gets neutralized, eventually the HCl would go in excess. If you add too much HCl, the solution would become acidic, and phenolphthalein would become colorless in acidic conditions. This would indicate that you should stop the titration because you are now adding too much HCl. So before the acid was added, phenolphthalein would give a pink color because this flask contains an alkali. And after the acid has been added, and once acid goes into excess, the phenolphthalein over here would change color and would become colorless. Now the question reads that 3 titrations were done. The diagrams below show parts of the burette with the liquid levels at the beginning and end of each titration. So he's given us the burette readings for 3 separate titrations. Remember that this is where titration was occurring. The HCl was being added to this NaOH, the leftover NaOH in this conical flask. So the titration values would represent the amount of HCl that's being added. Now 3 separate titrations were done to get more accurate better results. By taking out the average, you're going to get more accurate results. So we're going to figure out how much HCl is being added from the burette into the conical flask. So he's drawn this 3 separate burettes are drawn. Their initial values and their final values are shown, and 3 separate titrations are done. So we need to fill a table, the table given below, using these values. Now in the first titration, the initial value is 0 centimeter cube and the final value is 25.20 centimeter cube. So the initial is 0.00 centimeter cube. Remember to take burette readings to 2 decimal places. So let me correct this. The initial burette reading, this is the section for the initial burette reading, it's 0.00 centimeter cube, and the final burette reading for the first titration is 25.20 centimeter cube. So the amount of acid HCl that's added in the first titration is going to be the difference between the initial and the final value, which is going to be 25.20 minus 0.00. So the amount of HCl that's added is going to be 25.20. In the second titration, the initial value is 6.80 centimeter cube and the final is 31.10 centimeter cube. So it's 6.80 centimeter cube and the final is 31.10 centimeter cube. So the amount of acid that's added in the second titration is going to be the difference between the 2 values. So using my calculator, it's going to be 31.1 0 minus 6.80, and the answer that I'm getting is it's going to be 24.30 centimeter cube. Now noting down the values for the third titration, the initial is 23.8 and the final is 48.3. So it's 23.80 minus, and the final reading is 48.30. So the amount of acid that's added, so let's subtract the two values, 48.30 minus 23.80. And the answer that I'm getting is 24.5 centimeter cube. So it's 24.50 centimeter cube. So I've gotten three separate values of about the amount of HCl that's added in this titration that's happening over here. So in the next part, I need to take the best titration results. The best titration results are the ones that are close together, because the values that are slightly far off indicate that there must be something wrong in the experiment or something anomalous. So this value is slightly off from the other values. So your best titration results are the ones that are very close to each other. So these two are your best titration results. And in the next part, using these results, the average volume of hydrochloric acid required was, so we need to find the average volume. The average volume is going to be the average of the two values. So you have 24.30 plus 24.50, and I'm going to divide that by 2 to get the average, which is going to be 24.40 centimeter cube. So that's the average volume of HCl that's being used. So I figured out what amount of HCl is added on average, and I'm going to write that value down. So it's 24.40 centimeter cube of HCl on average has been used in, and this is my average value for taking my best titration results. So I know the concentration of HCl, which is 0.1 mole per decimeter cube, and I also know the volume of HCl. Now moving to the next part, you're asked to calculate the number of moles of HCl, calculate the number of moles of HCl, hydrochloric acid, in the average volume of 0.1 mole per decimeter cube hydrochloric acid. So we know the average volume, which is 24.40 centimeter cube, and we also know the concentration. So we can find the moles of HCl that are being added into the flask by using the formula that for solutions, moles is concentration multiplied by volume. The concentration is already given, it's 0.100, and the volume, the average volume that we have found is 24.40 centimeter cube, but that should be in dm cube. So I'm going to divide that by 1000, and I'm going to now calculate the value and find the number of moles of hydrochloric acid using my calculator. So the answer that I get is 2.44 into 10 raised to the power minus 3 moles. So the moles of HCl that are added, so let's write those down as well. So the moles of HCl that are added are 2.44 times 10 to the power minus 3 moles. So this is the amount of HCl that's added from the burette into this flask, which contains the leftover NaOH. So moving to the next part, he's told us that hydrochloric acid reacts with sodium hydroxide according to the following equation. So the ratio in which HCl and NaOH react is 1:1 according to the equation, which means that the moles of HCl and the moles of NaOH are going to be exactly the same. So we now asked to deduce the number of moles of NaOH present in 25 cm cube solution S. So going back to our question, our diagram, we know that 2.44 times 10 to the power minus 3 moles of HCl are being added from the burette. So the amount of moles of NaOH over here are going to be exactly the same. They're going to be 2.44 times 10 to the power minus 3 moles. The reason being that the amount of NaOH is going to be exactly the same. The reason being that the two are going to react in the same ratio. According to the equation, the ratio of HCl with respect to NaOH is 1:1. So the amount of moles of HCl and the amount of moles of NaOH are going to be exactly the same. So if HCl has 2.44 times 10 to the power minus 3 moles, then NaOH is also going to have exactly the same amount of moles in 25 cm cube in the flask. So the answer to this part is 2.44 times 10 to the power minus 3 moles. Now moving to part G, the question is now stating that using your answer in F, which is the previous part, calculate the number of moles of NaOH sodium hydroxide in 25 into 50 centimeter cube of solution S. So we found the moles of NaOH in this flask over here, and they came out to be 2.44 times 10 to the power minus 3 moles. The volume of NaOH or solution S was 25 cm cube in this flask. Now he's asking how many moles of NaOH are present in this 250 cm cube flask, this volumetric flask over here. Now this is pretty simple. You can use ratios. That you know that in 25 cm cube flask, this tiny flask over here, you had how many moles? You had 2.44 times 10 to the power minus 3 moles of NaOH. So how many moles would be present in the 250 cm cube original solution S? Now it's you can use ratios, or it's pretty obvious that you just need to multiply the value by 10, because the moles would be, the volume is 10 times 25 multiplied by 250 by 10 is going to give you 250. So the moles are going to be 10 times the amount. So it's going to be 2.44 into 10 to the power minus 3 multiplied by 10 would give you 10 to the power minus 2 moles. So that's your answer to this part. So the moles of NaOH would be 10 times that many, because the volume is 25 cm cube over here, the volume is 250 cm cube. So the volume is 10 times, so the amount of moles is also going to be 10 times. So we're able to find, let's write that down over here as well. The amount of moles of NaOH over here are 2.44 times 10 to the power minus 2, actually 10 to the power minus 2 moles. And let's highlight that. So that's the amount of moles of NaOH present in this 250 cm cube flask over here. In the next part, part H, you're asked to calculate the number of moles of NaOH sodium hydroxide in 50 cm cube or 1 mole per dm cube sodium hydroxide. So we are asked to find the moles. You're given the volume and the concentration. This is the NaOH that was added originally to this beaker over here. Remember this beaker over here, you were asked to add this amount of NaOH, which was in excess, to this beaker, and the moles of NaOH that we did calculate in the previous step, these are the moles of NaOH that were left behind, that did not react in with the organic acid T. There was an acid and alkali reaction that was going on, but we added too much NaOH and some of it was left behind. So we have found the leftover NaOH. Now we are asked to find the original NaOH that we added in this beaker. So you're given volume and you're given concentration as well. So volume and concentration is given. So we can use the formula that moles is concentration multiplied by volume. The concentration in this case is 1 mole per decimeter cube, and I'm going to multiply it by the volume, which is 50 cm cube. So that should be divided by 1000 and we will get moles. So using my calculator, it's going to be 1 multiplied by 50 and then divided by 1000, and the answer is 0.05 moles. So these are the moles of NaOH that were added initially at the very beginning. So it's 0.05 moles of NaOH that were added, that were reacting with the organic acid, but since it's in excess, some of it was left behind. And we've also calculated the leftover NaOH, which is 2.44 into 10 to the power minus 2 moles. Now moving to the next part, he's asking, by subtracting your answer in G from your answer in H, calculate the number of moles of sodium hydroxide that reacted with the original sample of the organic acid T. So now we are asked to figure out how many moles of NaOH were actually reacting with this organic acid. So again, once more, these were the moles of NaOH that were originally added to react with the organic acid, but since they were in excess, and these are the amount of moles of NaOH that were left over at the end of the reaction, and that were transferred to the volumetric flask. So the amount of NaOH that's actually reacting would be the difference between the two values. So you had 0.05 moles originally added, 2.44 into 10 to the power minus 2 moles were left behind. So taking the difference would be the amount of moles of NaOH that actually ended up reacting with the organic acid T. So it's going to be 0.05 moles which are my original moles of NaOH that were added, and 2.44 times 10 to the power minus 2 moles of NaOH were left behind at the end of the reaction. So using my calculator to solve this, it's going to be 0.05 minus 2.44 times 10 to the power minus 2, and the answer is 0.0256 moles. So going back to my sketch, we added 0.05 moles originally. 2.44 times 10 to the power minus 2 moles are left behind. So the actual amount of moles of NaOH that are reacting are not 0.05 moles that are reacting with the organic acid T over here. They are 0.0. The value that I calculated is 0.0256 moles. So 0.0256 moles of NaOH are basically reacting with the organic acid T over here. Now moving to part J, he's saying that given that 1 mole of T reacted with 2 moles of sodium hydroxide, so we have the ratio of NaOH with respect to T. He's saying that 1 mole of T, so if you have 1 mole of T, is reacted with 2 moles of sodium hydroxide. So the ratio in which these two are reacting is 2:1. And we have the moles of NaOH that are reacting with, which we calculated in the previous step. So if you have 0.0256 moles of NaOH, then what moles of T would be present? So that is what we are going to find, and we're going to use the unitary method, simple ratios, crisscross multiplying. Let's call this x. X would be equal to, it would be 1 multiplied by 0.025 and dividing that by 2. So if you divide 0.025, it's 256 actually. If you divide 0.0256 and you divide it by 2, the answer that you're going to get is 0.0128 moles. So this is the moles of, the number of moles of T in the sample. So it's 0.0128. So going back to our sketch, the amount of moles of T are 0.0128. So these are the amount of moles of T in this sample that we used. He gave us the ratio of NaOH with respect to T. It was 2 NaOH reacting with 1 organic acid T. So if you had 0.0256 moles, so the moles of organic acid T came out to be 0.0128 moles. Finally, in part K, you're now using your answers to A and G, calculate the relative molecular mass of the acid T. Now this part A was the first thing. We now know 2 things about the organic acid T. They're both given over here. We know the mass, which is 1.51 grams, and we also know the moles of organic acid T, which are 0.0128 moles. So these 2 things are known, the mass and the moles. So we can use the mass of the organic acid T is 1.51 grams, and the moles of the organic acid are 0.0128 moles. So they are known. So we can use the formula moles is equal to mass divided by the molar mass, which is mR. And using this formula, we can find the mR. We know the moles, it's 0.0128. We know the mass as well, which is 1.51. What we don't know is the mR. So solving for mR, it's going to become 1.51. Rearranging the terms, it's going to be divided by 0.0128. And the answer that I'm getting is approximately, the mR is approximately going to be equal to 118. Rounding it off, it's going to be 118. So after finding the mR, the last part is that the acid T contains 2 carboxylic acid groups and has the formula shown. So he's given us the formula, and it has 2 carboxylic acid functional groups, one over here and one on this side, one on the right hand side, one on the left hand side. And he's now asking us to figure out what are the values of X and Y, which is how many carbons and hydrogens there are in this carbon chain over here. So deduce the values of X and Y in the formula. Now we know the mR is 118. The mR 118 means that this entire thing, if you sum up all the atomic masses, it's going to be equal to 118. what I can do is I can get rid of the carboxylic acid from both sides because I'm interested in the X and Y. So if I get rid of the carboxylic acids from both sides, so I need to subtract the 2 carbons in the 2 carboxylic acids, so I have to subtract 24 from it. There are 4 oxygens, so I need to subtract 4 into 16. 16 is the atomic mass of oxygen, and there would be 2 hydrogens as well. So basically I'm subtracting 118. If I get rid of the 2 carboxylic acids, that's the AR, the combined AR would be equal to 90. So removing that would give me 28, which means that the remaining CXHY is equal to 28. Now the only way it would be equal to 28 is if I have 2 carbons, that would be 24, and I have 4 hydrogens, then that would be equal to 28. If I have 2 carbons, that's 12 times 2, that's 24. 4 hydrogens is 4, so that would be equal to 28, which means that this X and this Y over here, their values are X would be equal to 2 and Y would be equal to 4. So X is 2 and Y is 4. So the actual formula of this organic acid T is going to be, it's going to be carboxylic acid group on one side, there would be 2 carbons and there would be 4 hydrogens in the middle, and a carboxylic acid group on the other side. So the organic formula of the organic acid T is going to be this thing over here. Now the very last part of the question, part M, deals with organic chemistry, and it says that the sample of the acid T, which we have figured out to be a dicarboxylic acid over here, which whose formula that we figured out in the previous step, which is C2H4, with carboxylic acid groups on both sides, is reacting with an excess of ethanol in the presence of a small volume of sulfuric acid. Now ethanol and a carboxylic acid, they would end up forming an ester in the presence of a concentrated sulfuric acid. So I'm going to first write the displayed formula for the carboxylic acid that we figured out. So it had carboxylic acid functional groups on both sides. So there was a C double bond O and OH group on one side, and a C double bond O and an OH group on the other side, and he's reacting it with ethanol. Ethanol has 2 carbon atoms. It's an alcohol which has an OH group, and let's complete the bonds of carbon by bonding it with hydrogen. So it's C2H5OH, that's ethanol. So this is one molecule of ethanol, and this is the carboxylic acid functional group. What happens is the alcohol loses its hydrogen and the carboxylic acid loses its OH when they react. So let me rub those off. So we get rid of the OH and we get rid of the hydrogen in ethanol, and the H and OH, they go and they end up forming a water molecule, and these two then eventually bond to each other and they end up forming an ester link. So this over here is an ester link. It's C double bond O bonded to an O, so this is an ester link over here. But since this carboxylic acid had a carboxylic functional group on the other side as well, so there's going to be a reaction on the other side as well. There's going to be another ethanol molecule coming from the other side, and it's also going to bond with the carboxylic acid functional group on the left hand side of this molecule. And again, the same thing would happen. The carboxylic acid loses its OH, the alcohol would end up losing its H. We're going to rub these off, so we get rid of these, and the two would end up bonding with each other. The O would then complete its bond by bonding with carbon. So this is the organic ester that would be formed when the two substances react, and we need to write the formula of this. So it's going to be, so let's start writing from this side. The first thing over here is CH3, so that's CH3, followed by a C and 2H, so that's CH2, followed by an oxygen, then a C double bond O, so that's CO, followed by C2H4, then you have C double bond O, so that's CO, followed by another oxygen, then you have CH2, and after that you have CH3. So this is the formula of the organic ester that would be formed. And in the last part is, so that's pretty obvious, to which group of the compounds does the product belong? So it's an ester. It's an ester that we have drawn containing ester links.